Hello, I'm Michael Miljanovich, and this is an introduction to nondeterministic finite automata. What is a nondeterministic finite automata? An NFA is a DFSA, a deterministic finite state automata, where an input can lead to different states. Instead of being forced to follow the transitional arrows from one state to another, we have options. In this nondeterministic finite automata, when we reach Q0, we have the option, if we're given the input 1, to either stay in the same state or to move on to the next one. If there's any path at all that we can find that leads to an accepting state, then the string is accepted. Otherwise, it is rejected. Let's take, for example, this string here, 0, 1, 0, 1, 1, 1, 0. If we weren't really trying very hard, we can see one path that's through here is just from Q0 to loop repeatedly until we reach the end, but that's obviously not going to give us what we need. What we really want is for the last 1, 2, 3 characters to lead us out of Q0 into Q3. So we'll loop all the way through the 0, the 1, the 0, the 1, continuously staying in Q0 until we reach the spot where now we want to actually process these 3 inputs. So we loop through. Once we reach this third from the end 1, now we can proceed to Q1. Then this 1 lets us go from Q1 to Q2, and the 0 at the end lets us go from Q2 to Q3. How about another example? Let's suppose we have 1, 1, 1, 0, 0, 0. Here things don't work out quite as well for us. If we loop through until we reach the third last character, that leaves us with a 0. But for that, we have to stay in Q1. There isn't an edge we can take out of Q0 to go to Q1. So this means that this is going to end up not being accepted because we're not able to find any path that takes us from Q0 to Q3. If we were to jump the gun, in a sense, and jumps directly from Q0 on the first character to Q1, then to Q2, then to Q3, well, once we hit Q3, there are no inputs that we're allowed to go here without going to a dead state, so that would be rejected. Let's go over the formal definition of an NFA. So an NFA is a quintuple, just like a DFSA or DFA, with 5 components. First off, just like before, Q is a set of states, so Q1, Q0, Q2, Q3. Sigma is the alphabet, so 0, 1 for something that accepts only binary. Q0, or S if you prefer, is the initial state where you're starting out, and it is part of the set of states. F is the set of accepting states, so in this example here, that's just Q3, and it has the double circle around it. And finally, delta is again our transition function. Now, delta is a little different than it was before. Previously, it would tell us the result of passing an input from one state. So if we have some state that we're on, state Q, and we pass in an input A, this tells us what state we go to. But with a non-deterministic finite automata, we have more than one option. So this means that unlike a DFA, delta is going to give us a set of states that we can go to. If we look over here and we have Q to be Q0, this is the state that we're starting with, and we pass it the number 1, the end result is actually 2 states. It could either go to Q0 by following this arrow, or it could go to Q1. So the end result of delta of Q0, 1 is the set that contains both Q0 and Q1. Let's go through an example of an NFA. Suppose we have this language with words that have just the letters A and B in any number that we want, where the second last and third last characters of any word happen to be the same. So we need to develop an NFA for this language, and here's what it's going to look like. So let's go through this piece by piece so we can figure out what's happening here. First off, because we don't really care about anything except for the second last and third last characters, and the first N letters that we have up till that point can be any combination of ABC that we want, we start with our initial state that's going to loop back to itself with any combination of A, B, or C. We want this to be able to handle the case of the clean star, where we could have none of these, or we could have as many loops as we really want to. What we do care about, though, are the second last and third last characters. So this means when we're 3 from the end, we need to actually start considering what states we're going to end up with, and keep track of what that character is, because the character that follows the third last one, i.e. the second last one, needs to match. So we end up splitting into 3 different states here based on which character we're looking at. Since our alphabet only has A, B, and C, there are only 3 states we really need to worry about. So if the third last character is an A, then we need to keep track of that. The second last character is a B, third last character is a B, we need to keep track of that. Third last character is a C, we need to keep track of that. Then once we know what the third last character is by storing that memory, in a sense, in these states Q1 to Q3, then we see if those states also receive the same letter as they just did to proceed on to an accepting state. If we're at Q1 and we don't get the letter A, we get some letter that isn't the same, then this leads to a dead state. It means we're not going to accept it. However, if it is the same, then we proceed on to Q4, which then requires one more character since it's the second last and not the last, and that should take us to Q5, which is where it gets accepted. Let's talk about another potential component of an NFA, which is an epsilon transition. So reminder that epsilon basically means the empty string, so it means that there's no character being passed here. An epsilon transition is what you could call a free movement. If you're in Q0 in this diagram and you want to proceed to Q1, you can do so without spending any characters, without processing a symbol. You can transition for free, which is what this symbol means here. For the purposes of proving anything, if you want to show that you have reached or not reached a certain state, reaching Q0 in this diagram is effectively equivalent to reaching Q1 because the difference between these is nothing, the empty string. Also, any NFA that happens to have epsilon transitions can also be called an eNFA. For the purposes of this presentation, I'm just going to call them all NFAs in general, but you might want to distinguish between NFAs where they don't have any epsilon transitions and those where they do. Now, how do NFAs fit into our discussion with the rest of the class? Well, let's suppose we have L, some language over any alphabet sigma, then these statements are all equivalent to each other. There is a regular expression that matches L. There's a DFA that accepts L, and we discussed this in the previous presentation. And finally, there is an NFA and an epsilon NFA that also accept L. And proofs for these are all found in the course notes if you'd like to go over them, but I'm going to go through a few specific examples just to show you how these might be translated. Let's start out with the first translation from one to another. Suppose you have an NFA. How do you generate an equivalent DFA? So how do you go from one state automata where you have non-deterministic ways to go to one where everything is deterministic? The way you do this is using an algorithm called subset construction, and here's how it works. First off, you're going to start with a blank slate. You're trying to build DFA, so you're going to do so one state at a time, starting with the initial state and adding on states over and over until you've completed your state automata. We're going to define E of Q as a set of states that's reachable from any state Q by taking either 0 or more epsilon transitions. Since we said before that epsilon transitions mean that effectively they are the same state if we want to be able to reach one from another, we're going to care about the set of states that you can reach just by going through epsilon transitions without processing input from a state and use that as a label. So when we're building our DFA, we're going to be naming our new states, the sets of states that are equivalent in our NFA. And we'll see in a little bit exactly how this works. The starting state for the DFA is the E of S, where S is the start state of the NFA. So let's say that you have an NFA where you have one starting state, but it has an epsilon transition to Q1. When we look at our DFA, we're going to start out at a state where the name of it is both Q0 and Q1, because that's the set of states that you could start out with in your NFA without processing any input. For each state in the DFA that we're going to be adding on one at a time, we compute all of the sets in the NFA that you could reach if you had processed that symbol from whatever state you are currently working on. So I'll go through an example just so we can see exactly how this process works one step at a time. So here's our example. Suppose we need to find an equivalent DFA for the following NFA, which starts with an initial state Q0 and an accepting state Q3. Rather than having a diagram for NFA, suppose you're only given a table, and this shows you the states that you have to work with and their transitions based on input, which are the symbols, and the state you end up with. So we're going to break this down one step at a time and figure out all of the components of the DFA that we're going to be working with, starting from the very beginning, which is Q0. So let's start with our initial state Q0 and go step by step through building a DFA out of the information we have from our NFA. First off, just by looking at the chart, we can see that there are some epsilon transitions that we'll want to keep in mind. And from the initial state Q0, we can use an epsilon transition to reach Q3. This means for our DFA, the initial state that we're going to have can have the name, the set of Q0 and Q3. And when we're making transitions from this initial state, we need to consider both of those potential options for where we're going to transition. Next, let's look at what we can do if we're actually passing some input through the states Q0 or Q3. Suppose we pass it a 0. Well, Q3 doesn't show up on our table, so there's nowhere we can really go from there. But if we pass 0 to the state Q0, that ends us up in Q1. So this is a new state we haven't seen before, so we're going to add this to our DFA. Alright, now what if we pass a 1 to where we are? Well, if we pass a 1, the only result that we can go with is passing a 1 to Q0, since Q3 doesn't give us any options, and that leads us to Q0. But if you remember from before, the epsilon transition from Q0 also takes us to Q3. So really what we're going to have here is a state Q0 and Q3 that loops back to itself on the input 1. Alright, well, now that we have a new state Q1, let's go see what we can do from there. Well, if we pass Q1 a 0, since that's really the only thing that we can do with it, we end up with Q2. And we can see from the chart as well that Q2 has its own epsilon transition that goes to Q1. So this means that if we pass 0 to Q1, we can end up in the collection of states that includes either Q1 or Q2. And this is a state that we haven't reached before. Even though we've reached just Q1 previously, now we've reached a spot where we could be at either of these two places. So in our DFA, we'll consider this to be a new state. Now, what happens if we pass 1 to our Q1 state that we got from earlier? Well, this doesn't go anywhere. There's no entry on the chart for us, so this means that this is just going to lead to a dead state. Now, this dead state is new. It wasn't something we already had in our DFA, so we're going to add it to our automata because we didn't have it before. And later we will make sure that this state doesn't actually go anywhere just by not adding anything to it. Alright, we still have a new state here, Q1 and Q2, so let's go process what we can do from there. Well, if we pass 0 to Q1 or Q2, we can go over to our chart and we can see that, well, Q2 doesn't really go anywhere if we pass it to 0, so there's nothing really to do there. But if we pass 0 to Q1, that leads us to Q2. And just like before, we can follow the epsilon transition, and we can see it's just going to loop back on itself. So Q1, Q2, if you give it the input 0, it's just going to go back to itself. Let's suppose that we pass it a 1. Well, we can see that Q1 doesn't have anywhere to go if you give it the number 1, but Q2 will. It will, when given 1, it'll lead us to a new state, Q3, which we've not seen yet, so we're going to record this as well as a new state that we need to consider. So, where does Q3 take us? Well, Q3, if we give it any numbers, just goes to a dead state. There's nowhere on the table for us to take it, so it goes, well, nowhere. And similarly, if we pass it a 1, it also doesn't really go anywhere. So that ends up being it for all of our states. So here, what did we end up with? Well, the total states we have, looks like there's 1, 2, 3, 4, and 5 of them. And so we'll record the names of all of those states. Our initial state is, before we were starting with Q0, but from the epsilon transition we were able to get to both Q0 or Q3, so that is going to be our initial state in our DFA. And our accepting state before was Q3. Now, none of the states in our DFA include Q3 except for Q3 and Q0 Q3. So both of these are going to be accepting states. And that's what we're going to end up with our DFA. So now we can actually start to construct the diagram. So here I've simplified all of the connections that we have from each of the transitions to other states. I've just broken down removing some of the extra transitions that weren't necessary. Anything that involved an epsilon transition doesn't need to be there because DFAs don't have epsilon transitions. And also our dead state I just added to the bottom to include that no matter what input you pass it, it just goes back to itself, so it's empty. So here is what our diagram ends up looking like. So we can see that our initial state is Q0, Q3, which is an accepting state. This is where we're going to start. If we pass it a 0, it goes to the next state Q1. If we pass it a 1, it loops back on itself. From Q1, if we pass it a 1, it goes to this dead state, which is over here. If you pass it a 0, it goes to Q1, Q2, which is the name of this state. If we're at Q1, Q2, and we pass it a 0, it loops back to itself, which we can see over here. If we pass it a 1, it goes on to Q3. From Q3, any input that we give it, 0 or 1, leads to our dead state, so we're just going to add one transition here for either 0 or 1. And also, Q3 is an accepting state, as we can see from the second circle. Finally, our dead state, given 0 or 1, just loops back to itself, and so we end up with a correct DFA for our original NFA. Now let's try another type of translation. Given a regular expression, how do you generate an equivalent NFA? The way that you do this is using a technique called Thompson's construction. Essentially, you're building it piece by piece and using epsilon transitions to connect all the pieces together. So, for example, let's suppose we're starting with something really simple. Your regular expression is just a symbol. Well, starting from our initial state, if you pass it the right symbol, it goes to an accepting state. And if you pass it anything else, it goes off to a dead state and doesn't get accepted. This seems pretty straightforward. Let's suppose we want to use the regular expression A or B. Well, from our initial state, if we give it A, it will lead to an accepting state. If we give it B, it will also lead to an accepting state, and any other symbols that are involved are not going to take us where we want to go. Finally, if we wanted to do the combination of these, the concatenation of these specifically, where we have A or B, all you would need to do is connect this state here to this state over here. You would make this no longer an accepting state, and this would be an epsilon transition. So you're essentially, once you reach here, you now are effectively over here. And so that's the easy way to connect some of these pieces together. Let's look at a couple more pieces we might use for Thompson's construction. Suppose we want to do specifically the concatenation of two regular expressions. Well, just like I mentioned, you simply connect the two of them following a straight line, and your only accepting state is the one that you end up with. The state in the middle is not an accepting state. What if you want to use clean star? Well, since 0 is a potential option, it means that your initial state needs to already be an accepting state. You could just have the empty string for this A or B clean star, which means that when you start out, you may not need to add any inputs at all. Then if you add A or B, the transition should take you once again back to the same accepting state, and any other symbol that is not included would lead you off to a dead state. Here's an example using Thompson's construction. Suppose we need to convert a regular expression into an NFA, and a regular expression is A or B star C. So there are two halves of this that we're going to have to worry about for our NFA. So let's start with the very easy one, just the symbol A. Well, we know from the initial diagrams that to construct this, we simply need a starting state, Q0. If given the right symbol, it leads us to an accepting state. Any other characters involved with this diagram would not take us where we want to go. Now let's think about the second half of this. Well, we need any number of B's as well as a C at the very end. So first off, we're going to need to branch off from this original trajectory that we might have and pick a second half. So we'll use an epsilon transition to go a different way if we want to consider the other option of this regular expression. Now, looking at just B star C, we can look at however many B's we want to have, and we can stay in a state where we continue to accept them until we finally reach either a character that's not permitted or we reach the character C. Once you reach the character C, this should take us to an accepting state where we've matched the expression, and any other characters involved would not match. Finally, let's go through one of the trickier forms of transitioning between these equivalencies. Given an NFA, how do we generate an equivalent regular expression? The way that you do this is using an algorithm for state elimination. First off, we need to build our NFA into a new form that will allow us to do this algorithm, and then we can start breaking it down. First off, if the initial state that we have, Q0, has any incoming edges, we're going to modify the diagram with an initial state that has an epsilon transition to that Q0. This way we can isolate our initial state and make sure it's only by itself with no other concerns for transitions that could happen. Similarly for the end, if we find that there are either multiple accepting states or the final state happens to have outgoing edges, then we're going to make a new accepting state that's called F, and it's going to have transitions from all of the accepting states that we had in our original diagram, and we'll make it so that F is the only accepting state in our new diagram. Then, one by one, we're going to eliminate every state that we have, keeping track of what needs to be followed for any transitions to actually go through to let you go from one state to another, until all that's left is our initial state, the one that we added in our first step, and this state F at the very end, which doesn't lead anywhere and just is an accepting state. Before we try an example of state elimination, let's go through some of the simple ways that we can break down NFAs into making them a little bit smaller by removing states. First off, suppose we have a direct path transition from Qi to Qk to Qj using two different tokens, R1, which can be any regular expression, and R2, which is the second one. If we want to remove this middle state, Qk, all we need to do is concatenate these two together. This kind of makes sense. If you wanted to get from I to j, you would just need to add this expression concatenated with this expression. So, to remove this, all we do is remove this middle section and make an arrow that goes directly from Qi to Qj, and what we need to transition there is the concatenation of both these regular expressions. Now, let's suppose we have something similar, except now we have an extra loop here where a regular expression allows Qk to go back to itself as many times as we need to. Well, we saw from before that clean star is what allows us to have these loops in here, because we can have any number of R2s in our expression. So when we remove this process, in addition to having this term and this term concatenated, in the middle we're going to have any number of R2. So we have R1, any number of R2, which is why we have R2 star, and then we have R3 at the end, because we need to be able to go from our middle state to our final state. Alright, and last off we have this case where we have two states and we just want to make it so that there's only one transition between them and we don't have two transitions. This is pretty simple. We just replace these two arrows with an OR. So regular expression 1 or regular expression 2 can take you from this state to the second one. So let's buckle in and go with the final example. Let's say we need to generate an equivalent regular expression for the following NFA, and this one's going to be a bit of a doozy. So we have four states here, Q0, Q1, Q2, Q3, and there's a lot of different transitions between them, but we can see the only characters we need to worry about are A and B, and we can see there's at least one epsilon in here that we'll need to also keep in mind. So our very first step for this is going to be to see if the initial state Q0 has incoming edges, which it does. From Q1 we can go back to Q0, so we're going to need to add a new initial state with an epsilon transition to Q0. So we take this diagram, we're just going to add one new state. We have Q0 to 3, so let's go and add Q4. And Q4 has an epsilon transition that goes to Q0, and Q4 is our new starting point. So the second step is to see if there are multiple accepting states or if the final state has outgoing edges. In this case we have both. Q2 and Q3 are both accepting states and they have edges that leave from them to go to other places. So we're going to create a new accepting state, F, and we're going to add the transitions from our previous accepting states to our new one. So here's what happens. We'll remove this circle, and we're going to create Q5, and Q5 will have epsilon transitions from Q2 and Q3. So you can see that equivalently this is the same automata as we had before, since we can freely go from Q2 to Q5, which is an accepting state, meaning that any transitions that lead us to Q2 would be accepted, because we can just go straight to Q5 afterwards. Importantly, however, Q5 has no edges that go out of it, meaning that once we've reached this position, we have to stop. And that's the kind of thing that you're looking for a regular expression. Now that we've set up our diagram, we're going to remove one state at a time and update all the transitions as necessary. Our goal is to break this diagram down so that all that's left is Q4, which is our initial state, and Q5, which is our ending state. So we're going to do this first off by removing Q0. What does this mean? Well, we're going to need to make sure that all the transitions still remain intact once Q0 is gone, which means that any states that go to Q0 still need to be able to follow those paths to end up where they would otherwise. First off, we can look at what happens to Q4. If Q4 goes to Q0, well, we don't need to pass it any symbols to do so, but it needs to still be able to reach both Q2 and Q1. To get from Q4 to Q2, we need to go up to Q0 and then take the letter B. This means that once we remove Q0, we need to still have a path that goes from Q4 to Q2, and B needs to be the symbol that it's going to take to do that. It also could go to Q1, and to do so, it once again takes the epsilon transition, then takes the character A, and ends up in Q1. So we now can just add an edge directly from Q4 to Q1, and it's going to take the character A. Pretty simple. What happens to Q1 is a little bit trickier. Q1 needs to first off be able to follow this arrow and go anywhere that it needs to from here. So the most obvious direction it can go to is back upon itself. If we want Q1 to go back to itself, we need to pass it A to get here, and then another A to go back. If we wanted to remove the Q0 from this equation, that means we're going to need to add a loop that goes from Q1 back to itself, taking AA to get there. Any other way that it goes isn't going to work. Now, we also could follow this path to Q0 and take the B path to end up in Q2. So this means we're going to need to consider that edge from Q1 to Q2. Well, we have an edge already, right? The one that has the epsilon. But we also need to consider that we can use another path to get there and merge it with this one here. So if we take AB, the concatenation of these two characters, we can combine them with the potential of taking the empty string and using that as our direction to get to Q2. So what we end up with is a new path, is the same path with a new label. And here's what it's going to look like. So now we have AB or epsilon takes us from Q1 to Q2. Q4 can take A to get to Q1, which loops back upon itself anytime you're given the string AA. And finally, Q4 goes all the way directly to Q2 using B. Now let's consider what happens if we were to remove Q1 from everything. Well, first off, we have two states that transition to Q1 that we need to concern ourselves with. So first off, let's look at Q4. Q4 can take an A to get to Q1, and from there it can get to Q2. So what are the possible symbols that we could accept as a path that gets us from Q4 to Q2, not going the direction where we have the B? Well, we need to have an A at the front to go this way. Then we can have any number of combinations of AA. In other words, AA in brackets star will keep us in the spot that we want to. Then we also can add along AB or epsilon. So there's really three terms we're combining here. A, AA star, and AB or epsilon. And it needs to be in that specific order as well. We also need to concern ourselves with Q3. Q3 has a path that goes all the way back to Q1 and then to Q2 as well. And we can see that there is already a path that's there, but it's going to be a slightly different one. So we still have to consider that A is an option to get there, but we also need to consider this A taking us to Q1 and back over. So sort of like the way that we did before, we're once again going to combine the concatenation of all these symbols and build a little formula that will take us from Q3 all the way over to Q2. Well, it's going to look very similar. It's going to have A followed by AA star, because there can be as many of them as you want, followed by AB or epsilon. Now for the sake of brevity, we're going to combine these three-part terms with the paths that already exist. So to get from Q3 to Q2, we're going to have A or the three-part formula. And to get from Q4 to Q2, we're going to have B or the three-part formula. And here's what it's going to look like. So we have our three-part formula, which is A, AA star, AB, or epsilon. And we can see that same part over here, A, AA star, AB, or epsilon. Alternatively, you can just take the B, or in the other case, you can just take the A, and those were the paths that were originally there. However, we now have maintained the correctness of the diagram, and we've broken down two states. We just need to break down a couple more. So now we're going to get rid of Q2, and in doing so, we're going to generate a lot of pretty lengthy regular expressions. But in the end, all these regular expressions are really just concatenations of parts that we already have that exist. If Q2 is gone, there's a few paths we need to ensure that still exist. We need to have a way to get from Q4 all the way to Q5, as well as to Q3. We need to have a way for Q3 to loop back to itself, And we need to consider that there is now a new path from Q3 to Q5 that doesn't include this epsilon path. So let's go through each of these one at a time. To get from Q4 to Q5, we need to take this term here, that takes us all the way to Q2. We add on a B star because B can be added to Q2 any number of times and keep it in the same position. And then we can just add the empty string. So in the end, it's just this term with B star thrown onto it, and that will get us from Q4 to Q5. To get from Q4 to Q3, we have this term and the B star, and then we just need to add another B on top of it. And that's everything we need to worry about for Q4. So what about the pass from Q3? Well, from Q3, we take this term down here to get us to Q2. We still have another B star that we need to add on top of that. And then another B will take us back to Q3. So that's going to be a loop that just returns it to itself. In terms of ways to go to Q5, we already have one path, which is just epsilon. And the other way that we can go is to take this arrow down here, using this term, adding the B star onto it, and then once again adding nothing more. And here's what it looks like in the end. So our path from Q4 to Q5 is just the term we had before with the B star. The path from Q4 to Q3 is the term from before with B star and another B. To go from Q3 to itself, it's that lengthy term that it had to begin with, then B star, then B. And to go from Q3 to Q5, you can either just take epsilon, the empty string, or you can take the lengthy term and B star, and then you've made it to the end. Now, we just have to get rid of that one last state, and we've completed our regular expression. So in the end, we're just going to have Q4, Q5, and one arrow between them. However, the term that's going to be there is going to be pretty lengthy. First off, there's one half of the term that's pretty simple. It's this term up here. This part, by itself, is one of the accepted strings for our regular expression. So we're just going to have this plus the path we can take to go the other way. And what that ends up being is actually just the concatenation of this term plus this term with a star because it loops plus this term over here. And so here's what that ends up looking like. Looks like a pretty lengthy mess, but you can actually, if you look really carefully, you can see that you just have this first term that we looked at in the first path, this second term in the second half that has the star here because you can loop as many times as you want, and then this third term finally here at the end. And that's the long path that you can go, or you could have taken the shorter path, which is just this other term that we started with from before. And now we have a regular expression. This regular expression represents anything that would have been accepted by our NFA that we started with, and we did so just by breaking it down into one single path.